Today we start Unit 3B, which is about measurement and counting in chemistry. We're going to focus, first of all, on the basic idea behind measurement and some of the problems that crop up every time we measure and how we deal with them in chemistry and other sciences. And then we're going to talk about the units that we use and how we deal with the very large and very small numbers that crop up in chemistry. We're going to start out by talking about uncertainty, which is inherent in all measurements that are made. Some numbers that we deal with in chemistry are exact numbers. These are numbers that we know with certainty. Here's an example. For example, if I make the statement, there are 12 eggs in the bowl, that's a counting number. That's an exact number of eggs. And counting numbers are exact numbers. Another type of number that's an exact number is something that we call a defining number, a number that is a definition. If I say there are 1,000 meters in a kilometer, there's not 1,000 meters in a kilometer because I measured a kilometer with a meter stick. There's 1,000 meters in a kilometer because that's exactly how many are defined by what a kilometer means. So that's also an exact number. However, all measurements that you take give you estimated numbers, no matter how precise you are. Estimated here doesn't just mean sloppy, or you didn't do your measurements very well, or your measurement tool was poor. No matter how careful, no matter how precise, no matter how expensive and delicate your measuring tool, they're always an estimate. So we deal with this by talking about a couple of different issues. These are different but related to one another. Accuracy and precision. Accuracy is how close your values are, or your measurements are, to a true or accepted value. Precision, on the other hand, is how close your measurements are to each other. People use these in everyday language, accuracy and precision, as if they mean the same thing. But they really don't. Accuracy and precision are different. Let's take a look at rifles to get an idea of what they each mean. This is an example of two rifles that are both accurate. This rifle on the left is accurate because if you sort of average up those shots, they end up in the middle, in the bullseye. If you sort of average up these shots, they end up in the bullseye. One's way off and the other one's way off in the other direction, but on average all these shots are close to the bullseye. Same thing is true on the right hand side. This target shows shots that are also precise because they agree with each other. Both of them are on target. This one's not precise. The right hand side is precise. Here's a different situation. Both of these rifles are precise. The one on the left is accurate because it's centered on a bullseye. The one on the right, even though it's just as precise, is not accurate because on average it doesn't go through the bullseye. Now here's a question. If you had to choose between an accurate rifle and a precise rifle, which one would you rather have? Well, if you're a smart rifle shopper, you're looking for a precise rifle because you can always fix inaccuracy by resighting it or at least holding your rifle down and to the left in this case. But there's not much you can do about a rifle that's not precise. So precision is more important than accuracy because you can fix inaccuracy. Well, the idea of accuracy and precision comes into this next discussion. Sources of error. Where do the errors come from in our measurement? There are two main sources of error. One is called random error. Random error is just normal everyday fluctuations in the measurement as you take that measurement over and over and over again. Random error contributes to poor precision. Now, you can make random error better. You can improve that with better equipment, better technique, better training for the people who are making the measurements. But you can never eliminate it. It never gets eliminated. What contributes to poor accuracy is systematic error. Systematic error is built in to how you make the measurements. These are mistakes in how the measurement is being made or faulty measuring tools. These things lead to a consistent and repeatable error. But by changing the way you measure with a better lab setup, you can often eliminate systematic error or at least change to less important versions of systematic error. When we report a measurement in chemistry, we're not just writing down the numbers that define the measurement. We're also reporting how precise the measurement was. So what we do is we report all of what we call significant figures and nothing more. We don't report anything that isn't a significant figure. Here's what significant figures include. Significant figures are all the digits that we know for sure, ones that by our eye we can tell are right. Then one additional digit that's the estimate, and there will always be one additional digit that's an estimate because that's our random error. Here's an example of what I'm talking about. Using this ruler, I would say that this bar is 60 centimeters long. Here's what I know for sure. I know for sure that it's somewhere between 0 and 100 in length. I'm estimating that it's 6/10 of the way between 0 and 100, but that's just my estimate. So I write down 60, and I write it down this way without a decimal point to say that number is the number I know as an estimate. I don't have a 1 here because I have a 0 instead that's implied because I know for sure that digit. I know for sure I'm not up to 100. I'm estimating that I'm up to 6/10. So I write that without a decimal point at the end because that would imply different precision. This is one significant figure. Here's the same bar, only measured with a different ruler. In this ruler, I know for sure that I'm between 50 and 70. I can be confident of that. It's between 50 and 70. I'm estimating that it's halfway between 50 and 70, so I'm writing down that the bar is 60 centimeters long, but now instead of just 60, I'm putting a decimal point there. That is different than writing just down 60 with no decimal point, because that point is telling me I know for sure 6. I'm not so sure about the 0, so I'm confident about the tens place that it's somewhere between 5 and 7, and I'm estimating the 0. Same bar, different ruler. If we focus in on just this portion, we could say that the bar is for sure between 60 and 61 centimeters long, bigger than 60, smaller than 61, and then we'd have to estimate. Now I'm estimating that it's halfway between 60 and 61, and so based on that, I'm going to write down that this bar is 60.5. I'm including all the digits I know for sure. I know for sure the tens place is 6. I know for sure the ones place is 0. And I'm estimating that the tenths place is 5. So that's 3 significant figures. 2 I know for sure, 1 that I'm estimating. As we read other people's measurements, and as we write measurements of our own, we need some rules for how to handle these numbers. So here are 3 rules for reading measurements and for writing measurements using significant figures to report precision. First rule, any 0 that comes to the left of the first non-zero digit is not significant. So for example, if I had this number, 0.0001, or even 0.0001, that has one significant figure because all of these digits, all these zeros that come to the left of the first non-zero digit are not significant. If I have another number with even more zeros, that number this number has only 2 significant figures. All of these leading zeros that come to the left of the first non-zero digit, are all not significant figures. Here's another rule. Any 0 that comes to the right of a non-zero digit, but immediately to the left of an implied decimal point, is not significant. So I would write this number, 1000. If I wanted to show that I only knew it to the nearest 1000, I would leave off the decimal point. That means these zeros here are not significant. They have to be there because 1 and 1000 are not the same number. You need those zeros there to show what place your most significant digit is. But those are not significant. They're merely placeholders. If I write this number, 205,000, without a decimal point, that means I have 3 significant figures. Those last zeros, those trailing zeros, because they're to the left of an implied decimal point, one that's not really written there, that means they're not significant. The third rule is easy. Any other digit is significant. So that means all non-zero digits are always significant. Some zeros are significant, but anything that's not significant has to be a 0. Let's apply these rules and try to figure this out. How many significant figures are shown by this number, 786? Well, these are all 3 non-zero digits, so that means there are 3 significant figures then. How about this, 107.1? Well, here I've got a 0, but that 0 is not to the left of the first non-zero digit, nor is it to the right of a non-zero digit, but to the left of an implied decimal point. So that makes it significant. Along with the non-zero digits, that gives me a total of 4 significant figures here. In this number, I only have 1 significant figure. The zeros that come to the left of the first non-zero digit are not significant. So there's only one sig figure, and that's the 6. This looks like the same number we just had, but it's not in terms of precision. The zeros that come to the left of the first non-zero digit are not significant. But here we have two sig figs. Another way you know that 0 is significant is just think about it. There's no reason to write that 0 there. It doesn't change the size of the number. All it does is it tells whoever's reading it that you know this number to the nearest 100,000th, not just to the nearest 10,000. How about this one? It's a big number, but all the zeros that come after the last two, well, they're not significant because they're immediately to the left of an implied decimal point. If there really was a decimal point, that's where it would be. That makes all these zeros not significant, and it has only two sig figs. You only know this number to the nearest billion. The extra 9 zeros have to be there because 22 and 22 billion are hugely different numbers, but they're not significant in terms of precision. Try this one. Well, 105 has got 3 digits in it, and they're all significant. There's a 0 in there, but that 0 does not fit one of our two rules for which kinds of zeros are not significant. And so 105 has 3 sig figs in it. Now, you are not only going to read and write numbers in this class, you're going to have to do arithmetic. Add, subtract, multiply, and divide. So we have two rules for doing arithmetic using sig figs. One's for adding and subtracting, and another one's for multiplying and dividing. When you add or subtract, the answer that you get should have the same number of decimal places as the measurement in the problem that has the fewest decimal places. Here's an example. Say I was adding 10.2560 to this number, 10.4. Now, if I just grab my calculator and do this calculation, 10.2560 plus 10.4, my calculator tells me 20.656. But according to this rule, the answer has to have the same number of decimal places as the measurement that has the fewest decimal places that I'm adding. Well, this number here, the top number, is good to the nearest 10,000th. But the bottom number is good only to the nearest 10th. So I have to round my 20.656 down to 20.6. Here's our rounding rule that we'll use in this class. If the next digit is higher than 5 or is 5, we'll round up. If it's 4 or lower, we'll round down. Multiplying and dividing has a different set of rules. In multiplying or dividing, the answer has to have the same number of significant figures, not decimal points, but significant figures as the measurement in the problem that has the fewest significant figures. So let's say we were doing this problem. 20 times 506. Well, if I just do this on my calculator, take 20, multiply by 506, my calculator tells me 10,120. However, if I look at that 10,120 and think about my rule here, I'm supposed to have only one significant figure. So 10,120 has to be rounded to 10,000, only to show one significant figure. Let's do this calculation. 2.3 grams divided by 4.603 milliliters. Well, first of all, we can do something with the units. The units are grams per milliliter. Now let's do the actual arithmetic. 2.3 grams divided by 4.306 milliliters. My calculator gives me lots of digits, 0.53413841115. But in this problem, I have one number that has 2 sig figs and one that has 4 sig figs. I round off to the fewest number of sig figs in the problem. So that means my 0.534 something number just gets rounded to 0.53. Let's try this one. Now here's an addition problem. If I just do it on the calculator, 20 plus 273.15, my calculator says 293.15. But the rule that I have for adding and subtracting is I look at the decimal places. This is only good to the nearest tens place. This is good to the nearest hundredths place, but that doesn't matter. My answer has to be rounded off to the least precise of the two measurements in terms of significant figures. So 293.15, which is what my calculator says, that gets rounded to 290 because I have to round to the nearest tens place. Here's another one, 20,000 minus 5. If you're clever, you realize you don't even have to do this calculation. 20,000 minus 5. I'm going to round this off to the nearest 10,000 if I'm following my rule. 5 isn't going to matter at all. The answer is 20,000. It's hard to get used to this because in math classes, you're used to just using your calculator and reporting all the digits that your calculator gives you. But they're not all significant. They're not all important. Here's another one. 0.00406 times 1.08. Let's do the calculation. 0.00406 multiplied by 1.08. My calculator says 0.0043848. Both 0.00406 and 1.08 have 3 significant figures. So I round my answer off to 3 significant figures. I write down 0.00. Neither of those is significant because they come to the left of the first non-zero digit. Here's where the significant figures start. 4, 3, 8. There's my answer, reported to the correct number of significant figures. You try this one. 5.6 meters times 4.2 meters times 8 meters. Here's your answer. First of all, the units are going to be meters cubed. Nothing cancels out here. I just multiply meters by meters by meters. Now let's find the answer. See if you did this right. 5.6 times 4.2 times 8. Calculator tells me 188.16, but if you're doing your rules right, you know that multiplying these 3 together, that last one's only got 1 significant figure. So my answer has to have 1 significant figure too, so I'm going to round it off to 200 cubic meters. Try this one. Well, here's your answer. This is an addition problem. If I add on the calculator, I get 285 plus 5.32, and it's going to tell me 290.32. But here's what I know. Since this only is good to the nearest ones place, it doesn't matter that this is good to the nearest hundreds place. I got to round off to the least precise number. So that's to the nearest 1. I round my answer 290.32 to 290. Now I've got to put the decimal point there, because if I don't, it looks like I'm rounding to the nearest 10. So that decimal point is important in this case. Try this one. On the calculator, 13.000 divided by 14.3. Calculator gives me lots of digits. The top number here has got 5 sig figs. The bottom number's got 3 sig figs. So I round my answer to 0.909, which is 3 significant figures. I have units here. Miles over hours, miles per hour.